That's gone.
So you know to look at this, and if the concentrations are equal, the pH is equal to pKa, and it adjusts relative to that. Increase the concentration, it's going to lower the pH. You increase the concentration of HA relative to A minus. If you increase the concentration of A minus relative to HA, then that log is going to be negative, and negative is positive, and so your pH is going to increase, right? So if this ratio is positive, you get a lower pH. If that ratio, if that ratio is greater than 1, you get a lower pH. If this ratio is less than 1, you get a larger pH, which is the behavior that we expect. So I'm going to kind of take that equation and now look at the acid-base titration curves. See what happens on those curves. One of the first things that you'll note, and you probably remember from acid-base titration curves, is that as you add titrant to this system, you're assuming that you're we've drawn this curve assuming that we're titrating an acid with a base, and so pH is increasing as we continue to add more volumes or larger volumes of the base. We start off at some low pH, and we move through this point where the changes in pH kind of slow down. There's not a very large change in the pH with a given amount of base added, and the center of that kind of plane ends up being the buffer region, and the center of that is defined as the point that the ratios of the two concentrations are equal. So at this point, I didn't write it on the curve, I should have, sorry. At this point, the pH is equal to pKa. So this spot right here in the buffer region where the concentrations don't, or where the pH doesn't change much with concentration, pH is equal to pKa. Something to remember, I'm sure you probably already do remember, but the larger the magnitudes, the initial magnitudes of HA and A minus are, the less this ratio will change with the given number of moles of base added. So if you've got 1 mole of HA and 1 mole of A minus, and you add a half mole of base, this ratio is going to change by a large magnitude. But if you've got 10 moles of HA and 10 moles of H minus, and you add a half mole of base, this ratio doesn't change much at all, right? So the more HA and H minus you start off with in a system that you're trying to buffer, the smaller the changes in pH will be, or pOH, with a given amount of acid or base added to the system. Yeah? You guys remember that? So that's really easy to see looking at the Hasselbalch equation. Because this point occurs, or because at the point that this occurs, pH is equal to pKa, the suggestion is that a given system will act as a buffer the best for areas where you're trying to buffer close to its pKa. So if you want a buffer system that's going to keep you, in and around pH 5, you're going to look for a salt system whose pKa is 5, right? Because that'll be where that salt or that HA, A minus system ends up being most effective at maintaining pH. Yeah? So you pass the buffer region, you keep adding base. At some point, and you're using strong base, and you've got an acid system. At some point, you completely deprotonate all of the base, or sorry, all of the acid. The question is, where do you think the pH is going to be? And the answer is, it depends on what your acid was and what your base was, for that matter. we define this as a strong base in this case, so maybe we're working with sodium hydroxide or something like that. You take HCl and you add NaOH to it, you end up with H2O and NaCl, right? What's the pH of that system going to end up looking like? What's the pH of sodium chloride system? It's about neutral. It's because neither Na plus nor Cl minus does much to change the proton concentration or hydroxide ion concentration in solution. Neither one of those guys has a very strong ability to deprotonate water. Instead, Cl minus doesn't really deprotonate water, creating OH minus, so you don't end up with effects on that. But let's say that you had that system that we looked at earlier, H3C HC2 O minus. How does that work? C double on O. I can draw it organically. Right? This guy, acetic acid.
CH3O. CH3O minus.
That guy. So you stick that guy in solution, and you start titrating the base. That's acetic acid, right? It's the stuff that your wine turns into. You take that guy, titrate it with sodium hydroxide until you've added equal molar amounts of both. Now what do you have in solution? This guy becomes H2O, because these OH minuses pick off those protons and turn into water, and you end up with H3C2OO minus. And this guy is a weak base, right? And so at this point in the titration, where you've added equal molar amounts of base to the amount of acid that you started with, and you've completely deprotonated that acid, you've turned that weak acid into a weak base, and so you'd expect that if you looked up here at pH, this pH would be something that was greater than neutral, right? So it would be something above 7. If you were titrating a weak base with a strong acid, so here we're titrating a weak acid with a strong base, the kind of inverse titration is a weak base with a strong acid. At the point that, say, I guess the example that your book gives is if you titrate NH3 with HCl, at the end point of the titration, or the equivalence point of the titration, you've created a bunch of Cl minus and NH4 plus. What did we say ammonium chloride did when we stuck it in solution? It's a weak acid. And so at the equivalence point for this titration, titrating a weak base with a strong acid, you're going to end up with a pH that's somewhere below neutral, right? You're going to drop the pH. And so the pH at the equivalence point is going to end up being a function of whatever species it was that your titration ended up producing. If your titration ended up producing a weak base or a weak acid, a weak base is going to make the equivalence point pH higher than neutral. If you end up with a weak acid at the end point of your titration, then you're going to bring that pH down below neutral, below 7. And so all of that is kind of itemized down here, the expectations that you would have for these titrations being a function of whatever species you're left with at the end point of the titration. All right, well that pretty much covers chapter 8. I know that was a kind of a slam dunk and a rush through material, but I don't think any of this was anything new for you guys, so hopefully that was a halfway decent review. And next week we'll get on to something more thermodynamically oriented. We've got 12 minutes left or something like that in the period, 15 minutes left in the period. Let me dig up your homeworks here. There's your homework. If you guys want to work on it, I'd suggest that that's how you spend the rest of the period. I'm here. Your classmates are here.